The last part just takes 5 minutes, just really a remark. So maybe we can squeeze that in, unless someone has to run for a slot right after this. I do want to ask you, though, if you've seen something like this before. So maybe just on Slido now, if you've seen any way of balancing binary search trees. Maybe you can be more specific and say what ways. So what types of, yeah, that's one. Yeah, that's the other famous one. Okay, many have seen red-black trees, it seems. And many have seen none. And if we sum up all the different emoji, we might get more for none than what we have. All right. So this is something you can treat as a black box for this class. And because we're running out of time, I'll skip explaining the examples. The basic thing, what this is about, is we had binary search trees. If insertions come random and we don't have deletions, the height stays logarithmic. But in the worst case, it was linear, which is terrible. But there is a way to enforce the height to stay logarithmic. There are tricks and balances, and here are some examples that shown up. So these are AVL trees or red-black trees. Is one of those is usually shown. There are many others indeed, and many more ways to get this. But in short, as a black box concept, you can make a binary search tree worst case height logarithmic by just making the insertions, deletions a little smarter and enforce a certain invariant. And these are all different invariants. I explained this last year in a little more detail. If you're interested, you can check out the video from last year. For us, all that we need to know is that it is possible. We won't need how. And here's a quick summary of what we've seen in this section, especially the more interesting data structures, heaps, and binary search trees. So binary search trees can do a lot more operations. And indeed, they're, in a sense, a superset of the operations of heaps. So you might wonder, why do we need heaps if a binary search tree can do all of that and more? And the thing is, there's a few operations where binary search trees are slower. One is the construction. You can do it in linear time for a heap, and for a binary search tree, you cannot. And the second reason is the abstraction of a priority queue is like when we talked about bags as a restriction of stacks or queues, is sometimes useful to express the intent that you only need a priority queue and not a fully sorted, fully ordered symbol table. And so people found that if you stick to this abstraction of a priority queue, you can actually get both insertion and change key to constant time, even in the worst case. So this is fairly recent results, less than 10 years ago, I think. A very celebrated thing that settled a long line of research. So even though binary search trees, in the way that we implemented them, are not much better than heaps, they're better heaps, at least in theory, and some also in practice. So it's a useful abstraction.